In this video, we proved that the quadratic congruence x squared plus 1 is congruent to 0 mod p, where p is an odd prime, has a solution if and only if p is congruent to 1 mod 4. So we start by assuming that p to be an odd prime number and the congruence x squared plus 1 is congruent to 0 mod p is solvable. That is, there exists an integer a such that a square is congruent to minus 1 mod p. As p is an odd prime, p minus 1 by 2 is a positive integer, so raising both sides to the power p minus 1 by 2. Let's raise left hand side to the power p minus 1 by 2, and then we should raise right hand side to the power p minus 1 by 2. See that by law of indices 2 and 2 gets cancelled and we obtain a to the power p minus 1 is congruent to minus 1 to the power p minus 1 by 2 mod p. As a square is congruent to minus 1 mod p, it cannot happen that p divide a. If p divide a square will be congruent to 0 mod p, and 0 cannot be congruent to minus 1 mod p for an odd prime p. So we can apply Format's little theorem as GCD of a comma p equal to 1 or p does not abide a to the power p minus 1 is congruent to 1 mod p, and so 1 is congruent to minus 1 to the power p minus 1 by 2 mod p. Further, p being an odd prime, either p is congruent to 1 mod 4 or p is congruent to 3 mod 4. If p is congruent to 3 mod 4, then there exists a positive integer k such that p equal to 3 plus 4k for some positive integer k. And so it follows that minus 1 to the power p minus 1 by 2 equal to minus 1 to the power 3 minus 1 is 2, so 2 plus 4k by 2, that's equal to minus 1 to the power 1 plus 2k, and that's simply equal to minus 1. So from, let's say, congruence star, by congruence star, 1 is congruent to minus 1 mod p. Remember, p is an odd prime. And so p divide 2. 2 is congruent to 0 mod p, or p divides 2. That's impossible, which is impossible. Why did we get such an impossible case? That's because we are assuming p is congruent to 3 mod 4. If p is not congruent to 3 mod 4, then it must happen that p is congruent to 1 mod 4. And so p is congruent to 1 mod 4. So we did one side. How about the converse? Conversely, we assume p to be a prime number and p is congruent to 1 mod 4. Then by Wilson's theorem, factorial p minus 1 is congruent to minus 1 mod p. We need not say p to be an odd prime, because if p is congruent to 1 mod 4, then p must be an odd prime. If we look at the previous proof, then we are applying Format's theorem. Now, if we want to do the converse, then we will be applying Wilson's theorem. And by Wilson's theorem, factorial p minus 1 is congruent to minus 1 mod p. Now, how much is factorial p minus 1? That's the product of 1 and 2 and 3, 4, and so on. Somewhere we'll get p minus 1 by 2. Remember, p is an odd prime, so p minus 1 by 2 is an integer. And then if you add p minus 1 by 2 just 1, you will get p plus 1 by 2. And in this way, if you continue, then you will get p minus 3, and then p minus 2, and then p minus 1. That product is congruent to minus 1 mod p. We need to somehow produce an integer x such that x squared plus 1 is congruent to 0 mod p. Can we see the square here? You see that 1n minus 1 gives us minus 1 square, 2n minus 2 gives us minus 2 square, 3n minus 3 gives us minus 3 square. Let's do that. You see that p minus 1 is congruent to minus 1 mod p. That's right. And then p minus 2 is congruent to minus 2 mod p. We continue this way to say that p minus of p minus 1 by 2 is congruent to minus of p minus 1 by 2. P minus of p minus 1 by 2 is simply equal to p plus 1 by 2 mod p. Let's call this one to be congruence 1. Let's call this one to be congruence 2. And so on. Let's call this one to be congruence p minus 1 by 2. Multiplying p minus 1 by 2 number of congruence as shown above, we obtain so we are multiplying all the congruences. Minus 1 times minus 2 and so on up to minus of p minus 1 by 2. How about the left hand side? P minus 1, p minus 2, and so on up to this is just p plus 1 by 2. Of course, mod p. As we said earlier, somehow we want to use Wilson's theorem. See that how many times minus occurs? It occurs minus 1 to the power p minus 1 by 2. And then 1, 2, 3 up to p minus 1 by 2, that is factorial p minus 1 by 2. As we said, somehow we want to get square. If I multiply both sides by factorial p minus 1 by 2, what happens? In the left hand side, I get factorial p minus 1. In the right hand side, I get factorial p minus 1 by 2, whole thing square. So multiplying both sides of the congruence, of course mod p, by factorial p minus 1 by 2. So we multiply the left hand side by factorial p minus 1 by 2, and when we do so, we should multiply right hand side by factorial p minus 1 by 2. Aha, we get something square. And how about the left hand side? Left hand side, you see that you get factorial p minus 1. Factorial p minus 1 is congruent to minus 1 to the power p minus 1 by 2 times something square. modulo p. Okay, by Wilson's theorem, factorial p minus 1 is congruent to minus 1 mod p. Nice. So we can write this congruence as minus 1 is congruent to minus 1 to the power p minus 1 by 2 something square. We can say x square. Now, let's recall what we need to prove. If p is congruent to 1 mod 4, then we should be able to find an integer x such that x square is congruent to minus 1 mod p. Since p is congruent to 1 mod 4, p minus 1 by 2 must be even. And so, minus 1 to the power p minus 1 by 2 must be equal to 1. And so minus 1 is congruent to p minus 1 by 2 factorial whole thing square mod p. So we got the solution for x equal to factorial p minus 1 by 2, comma, we find minus 1 is congruent to x square mod p, or x square plus 1 is congruent to 0 mod p. And indeed, we complete the proof.